Hello, we're Group 9 and we'll be looking at the analysis and redesign of a portable camping grill. So our product is the portable camping grill, and you can see in the folded view, this is how the consumer receives the product. They then are able to assemble it and build it to its standing position to use to cook, and we believe that about 50,000 units are produced a year. This is the exploded CAD view, and this shows more detailed all the parts that are included in this product. For our primary customers, we believe this will be recreational campers who do not have a lot of storage and want something light and easy to use. They also would want a product that has an aesthetic that's nature forward and good for camping. Our secondary customers are backpackers or hikers who need something light to carry on their backs when they're hiking and are not able to have access to electricity or gas to cook. Functional analysis, we started with cooking food. We then went into applying heat and access of food. For applying heat, containing heat and maintaining heat is key, and that comes from refueling fuel, monitoring temperature, and controlling airflow. For access to food, that includes position and removal. Then there's also assured dependability, assured convenience, and enhanced product, as well as please senses. So for our function component mapping matrix, there are position, food, allow folding, and contain heat that all have 3 or more parts that go into this, and allow folding has 7 parts that are included in this. For the product family design, the functional differentiation table, we look at what's similar and what's different for each customer group. With similarity, we see things like containing heat, position of food, and allow folding. And then differentiation comes through the show of aesthetics and control of airflow. For the component commonality table, we look at platforms, which are common parts between all variants, and then modules, which differ. Some modules include the legs, vent cover, and nameplate. Here you can see the original product versus what we have redesigned for our secondary group. We have removed the vent adjuster, nameplate, and also have redesigned the legs. Here is the standard interface of the legs. For the product family design, we have our original assembly diagram, and it was important to note here that the secondary design has no vent cover or nameplate. For our modified assembly diagram, we have moved our locking flanges and grill top earlier in the sequence because they are a platform, and then we have improved our delayed differentiation by moving the vent covers much later in the sequence.
So now we'll move on to design for manual assembly with a quick cost estimation. The total assembly time was found to be 692.68 seconds with an efficiency of 0.065. And from this, we chose 2 parts to be redesigned, one a platform, the side panel, and one a module, the legs, both of which fall on the high functional importance and high manufacturing cost in the quad chart here. Moving on to the changes made. So for the platform and side panel, we removed the handle fasteners and switched to bent sheet metal loops, and then also added this crossbar across the handle to remove any chance of tangling. And then for the module, the legs, we removed tangling art, and then also the radiuses on the bottom of the feet to reduce tangling, and then increased or created radius within the inside of the leg. These all follow the design guideline improvements of DFA 1, reduced parts, DFA 2, reduced fasteners, and DFA 8, reduced tangling. Now, a quick cost estimation for the final redesign. So for the total assembly time, it was almost half of the original at 370.16 seconds. The efficiency is almost double at 0.1216. And the redesign has clearly a positive influence on the product cost because of the reduced assembly time and virtually no impact on the product function.
For automated assembly, we selected the subassembly of the side panel and lock flange. And evaluating this at a feed rate of 5 parts per minute, we found the assembly cost to be 7.74 cents per part. When it came to making changes, we actually decided to remove the lock flange assembly entirely because it isn't actually necessary to its main function of holding the shape of the side panels. The grill top can accomplish this, and this is shown in the next slide. In addition to removing the lock flange, we also filled in the top lip, which altogether followed the DFA 1, DFA 2, and DFA 8 guidelines. Because we removed the entire assembly, the new assembly cost is now $0, and a photo of the new side panel is shown here.
For process selection, we decided to look at the redesigns done in the DFMA stage, namely the handle and the side panel. Starting with the handle, we based our tolerance on the fact that the handle must pivot inside of a sheet metal mounting. This means that we have sort of a middle-of-the-road tolerance at 0.5 millimeters, as the that's really the only interface with the rest of the assembly at the pivot. The main dimension is the thickness, which is 4 millimeters. You can see in our process selection matrix the only two criteria that passed are die casting and machining. For this part, we think that die casting would be a more viable option just based on the geometry of the part. For the side panel, we base our tolerance on the fact that this must fit between several other parts and it has to pivot between them. With this in mind, we decided of a tolerance of 0.013 millimeters, which is relatively small. The main dimension again here is the thickness, which is 1.5 millimeters, standard sheet metal. Based on these properties, sheet manufacturing is the optimal choice. If you look at the process selection matrix, this is evident.
We'll go ahead and start the design for manufacturing with the side panel redesign from design for manual assembly. So the material cost was $304, operating cost 38 cents, die cost 18 cents for a total cost of $360 per part. Moving on to the redesign, DfM Pro recommended a couple of things, which were that the bend radius over thickness ratio be greater than or equal to 2, and the edge distance from the edge of the hole to the edge of the flange, that over the thickness be greater than or equal to 2. And here we've got a drawing with some annotated features. So we increased all bend radiuses to 3 millimeters, DFSM 8, avoid sharp bends. We increased the tab width, DFSM 7, avoid narrow features, and then move back the hole in the tab, DFSM 7 and 8, avoid narrow features and 2 small holes. And all of these help the part meet the DfM Pro guidelines. And then a quick cost estimation for the redesign. So material cost is $305, up 1 cent, operating cost 38 cents, no change, and die cost 20 cents, up roughly 2 cents, for a total part cost of $362, up about 2 cents. So here's a quick comparison. Hubs using a power series transfer 100,000 units, predicted with a 20% profit margin that the before and after designs would both have a cost of $16.73 per part, and Hubs overestimates because it's primarily on-demand manufacturing, and so they use things like laser cutting that are cost-effective for small batch sizes, but not for mass manufacturing. And then finally, cost savings are not apparent here, but will show in real-life manufacturing, because DfM Pro primarily focuses on manufacturing reliability recommendations, which won't show here, but will show later down the line in manufacturing.
The second part that we redesigned with DfM analysis was the handle of the grill. The handle is die cast, and Zamek was chosen as the material. For the original part, the material cost was 15 cents, the operating cost was 29 cents, and the die cost was 11 cents, for a total cost per part of 55 cents. We redesigned this part by implementing DFDC rules. We eliminated sharp corners using DFDC2, we maintained uniform part thickness by removing ridges in the handle using DFDC4, and we eliminated side pulls using DFDC6. For the redesigned part, the material cost was 14 cents, which is slightly lower due to a small amount of material being removed from the handle. The operating cost was 28 cents, which is also slightly lower because the part could be made on a smaller die-cast machine. The die cost was 9 cents, which is also a decrease from the original part cost because of a less complex die and no side pulls required. This resulted in a total cost per part of 51 cents per part, which is 4 cents or about 8% less than the original handle design.
Based on the product shown after the design for manufacturing changes, a potential service that could be integrated to form a product service system is a firewood and lighter delivery service from sustainable loggers and suppliers. Currently, the product does not provide any fuel or flame to start the fire. The user must acquire fuel and provide their own ignition device to be able to use the grill for its intended primary function of cooking food. Therefore, by including this delivery service to the user's desired location, like a home or a campsite, not only is the customer's experience improved by making it easier for them to use the product without any extra tools, but customers' costs are also reduced by negating the need to spend time collecting firewood or buying some sort of lighter. In addition, by limiting service partners to sustainable loggers and suppliers, the risk of users overlogging the surrounding areas is reduced, decreasing the impact on the environment. Overall, we applied DFA and DFM ideas successfully to this grill. Not only were we able to reduce part counts, like negating the need for log flanges, but we also improved the shaping of high-importance parts like the side panels and legs for easier sheet metal working. The major pro of our redesign is the reduced manufacturing and assembly costs while maintaining many of the functions of the original, like accessing food on the grill top and containing heat. However, because of the reduced costs, the biggest con is that some of the customization and aesthetics were lost, like the nameplates, fire decorations on the side panels, and nature depiction on the grill's legs. If we were to start over, we would probably choose a product that provided more variance in the manufacturing methods involved and more parts to modify overall. The grill was mostly made from sheet metal and was somewhat limited in terms of what we could change to improve it for manufacturing. Thanks for listening.